So vector-based search, I think, how many people in the room are familiar with vector-based search? Raise your hands. So everyone is familiar with vector-based search, so we just keep this slide. We don't need to talk about this. I mean, from the online audience, what you do is you encode your documents, your text in your index to vectors, you then build the dedicated data structure to search vectors in your index. This can be like a proximity graph, for example, or whatever other approach you want, like trees or hashing. And at query time, you encode your query to vectors, and then you run a k-nearest neighbor search. One of the biggest problems of vector-based search is, in general, low explainability. We have high dimensionality, so vectors are very long sequences of numerical values, 700, 1500, whatever, not really easy to understand from a human perspective. Each dimension, so each element in the vector has not clear semantic in most of the cases, so you can't really understand the tens feature, what it means, if it's a 0.78 or a 5.11. And each value of each feature is not obvious how it impacts relevance. So like it's higher number for the 11th feature better or worse in terms of any kind of meaning. So right now, most of the times, like vector-based search engine, they will just tell you this result is within the top K. The research is happening is still an open problem. Of course, we've seen like many other variations, like with Corbett, for example, or learn sparse retrieval, where you can get back some lexical terms individual. Still, you will have a neural model behind the scenes, not easy to explain. Parser more. Lexical matches. Even, I mean, people expect lexical matches to happen. So you have your keywords in your query. Even if you know that you're running semantic search, your user will likely expect some keyword match happening. And with vector-based search on its own, you can pretty guarantee that your keywords are going to be there. We implement projects for clients, and with some vector-based implementation, we got complaints like why the document with this keyword in the title is not coming up. And it's not easy to answer this kind of question. It's not easy to even fix these kind of problems, only with vector-based search. Low diversity. So vector-based search just returns the top K order by vector similarity, unless you add more logic on top, which could be, for example, the clustering mark as shown. It's not really easy to diversify. So the top K will be the closest to the query vector. So probably very similar to each other. So unless you add more logic on top, you would expect low diversity by definition in your top K results. So what is receiver rank fusion? So first of all, I would say it is currently a mitigation of the problems we've seen. Is it here to stay? I don't know, because vector-based search can improve maybe dramatically in the next few years, next few months, maybe. Still, it's a way of combining different queries. So not necessarily just a mitigation of the problems we see. So it's still like an additional tool that can help within your search. And how does it work? You retrieve, I put in here two sets of candidates. It's the most likely example, but actually it's just any number of candidates sets. One set can be from lexical matches, for example, with query keywords. Another set of results may be vector-based search, so k-nearest neighbor search. So you retrieve these two sets of candidates, you measure them and rank them in some way. Oops. So you take input multiple ranked lists, so ordered list of items, and you return a unified result set. The reason it's called reciprocal rank is because the inverse of the rank of the document in the ranked list will impact how these elements will be in the final result set. The higher the ranking in one of the input ranked lists, higher the contribution to the final result set. Residual rank fusion was introduced first time by Cormac in 2008, no, 9, sorry. Let's figure it out. So the algorithm is quite simple actually. So you start from a 0 score, then what you do, for each of the queries, you go with you scan basically the results in each of the queries, and you assign a score to that specific document, which is this formula, so it's the reciprocal of a constant plus the rank of the document in that result list. So I will have in here an example. We assign as a constant 10 just for simplicity, and we have 2 ranked lists in it. So in the first ranked list, we have item 10 at the first position, item 7 at the second position, item 9, 5, and 3. In the second ranked list, we have at the first position ID 7, so the 7th document, then document 5, document 9, 4, and 10. To find the score of each of these results in the final result set, what we do is we sum the contribution from each ranked list. So the document 7 will have a contribution of 1 divided by the constant plus 2 for the first ranked list, and a contribution of 1 divided by the constant 10 plus 1 from the second ranked list. I forgot the parentheses, but anyway, the 10 plus 2 is at the denominator of that fraction. And then we calculate the score of all the documents in this way. So the document 10 has a contribution of 1 divided by 10 plus 1 from the first ranked list, and a contribution of 1 divided by 10 plus 5 from the second list. So as you can see here, we don't care about each element score, but we just care about each element position. This is a limitation potentially of residual rank fusion, but it is what it is. So it is a simple way of combining ranked lists based on the ranking of the elements in each of them. So this was not possible in Solr, and in general, we couldn't combine easily different complex queries and then just merge the result sets. There has been in learning to rank in Solr, which is a way of ranking results, re-ranking results actually based on a machine learning model, the possibility of interleaving multiple machine learning models. Interleaving is similar to a certain extent to residual rank fusion. In interleaving, you interleave results from different result sets, normally for evaluation purposes, actually. So residual rank fusion is to present them to the user just for quality reasons. Interleaving is for evaluation, but it's similar. So interleaving for learning to rank only was possible in Solr. With this contribution, I wanted to add this capability in general for more than one query, so not only 2 queries, for any kind of Solr queries. And this is the proposed syntax. So you express in JSON your queries labeled, you can give names, and just for debug purposes and explainability purposes mostly. And you just pass an array of these queries. Actually, it's a map, because it's like the label plus the query with the query parser, for example. They can be like, as I said, the same kind of queries, so traditional keyword-based search, or maybe one can be like a vector-based one, and one is additional search. And trivia, this was already available actually. So query support, so this JSON object support was originally there to be used for faceting and specifically for domain exclusion, so a sort of refinement of counts within facets. So I didn't have to add the JSON support, so it was already there. And I just added parameters like the combiner to enable the combination and up to parameters to specify how many results you should consider for each rank release. So this is the global syntax. We've been in the last month discussing with other committers potentially to do this to a query parser, but even if it's a query parser, we pretty much present the JSON API will look similar to this. The parameters we support the algorithm, which the first algorithm will be just residual fusion, but we give the possibility to users to, actually not users, contributors, let's say, to add different algorithms in an easy way. So we support that framework by default, so with the contribution up to, so you may specify just a subset of the results from the original release. And then the constant by default is a magic 60, which was from the original paper. You know, not much discussing about that. It's configurable if you want to use another one based on experiment from actually and empirical results. You can do it. And about the internals, this is more for contributing. So if you want really to contribute to these pull requests, the JSON part is in this specific Solr class, the request to kill. As I said, we didn't really change it that much. Then at the moment, the main changes happen in the query component in Solr, which is actually quite an overcrowded component, to be honest. So it was not the ideal place, but it was the only place pretty much. And this has, the scope in here is to prepare the queries, or parse the parameters basically for all the queries and parse the queries in the JSON, and then process the queries effectively combining the results. So the process in the query component will then call the receiver rank fusion algorithm, which specifically is implemented as an implementation of queries combiner, takes in input an array of queries, a list of queries, and the results for each query, and another couple of Solr specific components that, if you're not familiar with Solr, you can just ignore it. It's more if you want to contribute. Then we have the implementation of receiver rank fusion, which is again in a dedicated class, so quite modular, quite easy if you want to change it or if you want to add another implementation. And the current limitation is the fact that at the moment, there is no support for grouping or field collapsing. So grouping is efficient in Solr that allow you to group search results potentially by the same field value, or field collapsing pretty much the same, but it's grouping gives you results like with a different format, which are grouped, while field collapsing will give you search results with the same normal format, single search result, but they are collapsed. So effectively, you just have one group head, and that's it. So you will get the result list, which is as the normal result list, but actually each element was the group head of its group. And the distributed search support, it is included. So in the first contribution, we will have distributed support, but this will happen per node, which is not ideal. So what we want to do is actually in a later stage to implement receiver rank fusion after you collect the results from the different nodes. Now, before we go to questions, we'd like to talk about the explainability part and the debug component specifically. So we have two layers of explainability, and I'm talking in here explainability for power users. So for the engineer that is maintaining the search engine. So I'm not really talking about like explainability for final users. So this is more for debug purposes, basically. So we have two layers within the debug purposes. Query parsing, so we want to see each of the query involved in receiver RM fusion, how it is parsed, and results explanation. So why we got in the final result set this document at this position. So we want to see how the multiple results were combined and the original scores. So this is an example of the query side. So we have a map again, basically, with the label, which is the same label you put in the JSON request, with the query string, and then what happened from query parsing wise. So I didn't change much actually. I mean, this is for single queries, this happens already in Solr. So for single queries, you will have just this block. So the query string, the query parser is, how the query was parsed, and then the toString from within. And this is actually pretty much just a loop, a for loop. So you just get this explain for all the labels, for all the queries involved in receiver and fusion. And for results debug, so you want to see the final score, and I want you to try to keep it as simple as possible. So you get, this is why you got this score. So 1 divided by the constant plus the ranking, plus 1 divided by the constant plus the other ranking, because its ranks were first for query lexical, 2 for query lexical 2. So here we get again the labels from the queries. So you can quickly say, take a look and see like, okay, this item is at this position because it was first for the lexical query, for example, and second for the query lexical 2, vector, whatever label you chose. Then you get the original scores. So then you get, for query lexical, this was the original score with literally the explanation of the original score. So nothing new there, is literally just the receive debug from that original score. So Visual works on what happened in the last month. So we've been discussing the pull request with other committers, specifically mostly David Smiley from the Solr community, to try to improve this. And actually also Osman participated from the Lucene and Solr community. We want to add distributed tests and better documentation. This is just to merge the pull request. So distributed test plus documentation, and potentially we want to ease the way it's currently integrated. So maybe a query parser, maybe less changes in the query component, but these are low-level details that are not important probably for the audience right now. Then after we have it in, and users can use this feature, we want to then extend it and better distributed support. Yeah, hopefully we want to do this, as I said, after distribution rather than per node. Field collapsing and grouping. Yeah, we want to support this in the way that you can do first field collapsing and grouping, and then you do receiver RAM fusion. And maybe additional algorithms. So maybe we want to extend receiver RAM fusion with weights, maybe based on the original score, or completely different algorithms to manage result sets.